At this point in the course, we should have a sense of what molecules are and some of the varieties of molecules that we can get, including things like isomers, which are different versions of molecules that have the same molecular formula. In this module, we're going to explore the role of electrons in that bonding and how those electrons disperse themselves throughout a molecule and the effects that that has. We're going to start off by talking about electronegativity and bond polarity. Our learning goals for this will be to understand the concept of electronegativity and how it's used to describe bond polarity. And we're going to use the Pauling scale to actually quantify the degree of polarity in different bonds and be able to predict what kinds of bonds are formed between two elements. Not all covalent bonds are equal. That is to say that while they share electrons, they don't always share electrons in the same way. This is something that's going to lead us to the concept of electronegativity, and to illustrate this, I want to consider two possibilities. This possibility is one where we have two of the same kind of atom. They have the same nuclear charge, plus Z, and there's an electron in between. You can imagine that this electron is shared pretty equally between those two atoms. It's a completely symmetric arrangement for the electron and the nuclei. But what if we had two atoms that are not the same? They have different nuclear charges. Now we might consider the fact that the electron is feeling a different degree of attraction for those two nuclei. Electronegativity is basically the measure of the difference in this attraction. So we can describe it, if you will, as the relative attraction of an atom has for one of the other bonds in a covalent bond. But it only applies to these elements when they are in a covalent bond. This is not a property of elements themselves, but simply a property that they have when they are bonded. So this concept of electronegativity is actually based on certain theoretical concepts that themselves are parameterized by experimental observables. It is a relative but not an absolute measure. So there are many different ways that we could measure electronegativity, but they're all measuring sort of the relative propensity of two elements. They only apply to atoms in a covalent bond. This is important to remember. You do not apply this to an atom that is just sitting by itself. It has no electronegativity then. While different models are generally consistent, they show the same kinds of trends. So here's a mock-up of the periodic table, and electronegativity is going to increase as we go up and to the right. So notice this is equivalent to going to smaller atoms. So in general, you could say that the smaller an atom is, the more likely it is to have a higher electronegativity. That, of course, excludes the noble gases, and since they do not participate in covalent bonding, their electronegativity is basically zero. All right, one of the most commonly used scales for electronegativity is one proposed by Linus Pauling, a famous American chemist who actually won 2 Nobel Prizes, one for chemistry and one for peace. In his scale, these are the numbers that are assigned to the various elements. Now, of course, he's assigned numbers to all of the elements in the periodic table, and I'm only showing the ones mostly in the upper right-hand corner. But I want you to see that, in fact, those nonmetals that we find in the upper right-hand corner tend to have higher values of electronegativity than the metals that you'll find over on the left-hand side of the periodic table. In particular, fluorine has the most electronegativity, around 4. Oxygen is the second most. So as we increase going up and across, we can assign relative electronegativities of these elements as follows: that fluorine is the most, going down to boron, and then I haven't included the metals, but they would all be much lower than these. These are essentially all of the non-metals that we have to worry about in this course. Polar covalent bonds are created when we attach a covalent bond between two atoms that are different. In other words, two different elements. Okay, polarity of these bonds means that the electrons are not shared equally between those atoms. They favor one side of the bond, and that causes one atom to be partially negative charged and the other atom to be partially positive charged. An example is hydrogen chloride, where hydrogen is much less electronegative than chlorine, so the electrons tend to lean in the direction of the chlorine. So we end up with a partial positive charge on hydrogen and a partial negative charge. Now, this notation that I've used here with using the Greek letter delta is simply meant to indicate that we don't have a full charge separation. In other words, hydrogen doesn't have a +1 charge. Delta is a number that's between 0 and 1. So it's sort of a gradual measure that we can use to tune exactly how polar this bond is. If hydrogen had a +1 charge on this molecule and chlorine had a -1, this would be an ionic substance. We're going to use this to quantify bond polarity, and in fact what we're going to do is say that the difference in the electronegativity between two atoms gives us an idea of how polar a bond might be. So using the Pauling scale, we might develop this following rubric for determining bond polarity. If the difference between the electronegativity of two elements is less than 0.5, we're simply going to say that's a covalent bond. It's nonpolar. There's not a great enough difference for the electrons to lean one direction or the other. However, if it's between 0.5 and 1.5, we're going to classify those bonds as polar covalent. That is to say, they are shared electrons, but they definitely lean toward one side of the bond. If it's between 1.5 and 2, that actually sort of elevates to another category, which I'll call partial ionic. It has some covalent character, but the charge is becoming more and more separated between the atoms. And then if the difference in electronegativity is greater than 2, then we'll call that definitely an ionic bond. Now there's nothing magic about these division lines in these differences in electronegativity. This is just a rough guide that you can use to sort of assess how polar a bond might be. All right, so once again we look at these Pauling electronegativity values, and you can see that anytime we have a nonmetal attached to a metal, we're likely going to have an electronegativity difference that is greater than 2, certainly very large. And so that's what gives rise to these ionic compounds. So as an exercise, I'd like for you to try classifying the following bonds according to their degree of polarity. Now to help you, I'm going to provide you with both the Pauling electronegativities of these elements as well as the rough guide that we have created on the previous slide. So take a chance, pause the video here, and come back and we'll discuss each of the bonds. All right, I hope you've had a chance to do this. Let's look at each of these bonds. Carbon and sulfur. The difference in electronegativity there is 0.03, so that's clearly a covalent bond, and it's nonpolar because the difference in electronegativity is not very great. Carbon and oxygen, however, have a difference of 0.89, so that's going to be a polar covalent bond, and indeed in a lot of the molecules that we will see in this course, carbon-oxygen bond is highly polar. Between carbon and hydrogen, it's 0.35. That's still below 0.5, so it will be a nonpolar bond. Between carbon and chlorine, it's 0.61, so like the carbon-oxygen bond, this too will be a polar covalent bond. And finally, between carbon and sodium, it's 1.62, so that gets us into that category of partially ionic. That is to say, it has some covalent character, but it's partially ionic. And it may surprise you that carbon forms a bond to sodium, and it's not ionic, but it's leaning in that direction. So I hope this has given you some insight on how to classify the polar covalence of different bonds, because we'll be using that concept quite a bit.